with my colleagues from Glaciares, from IRD. Maybe some of you know this place in south of Peru. It's Coropuna. And I think, I'm not sure, but I think I took this picture with Marius a long time ago. I will show you some basic things about glaciers and climate relationship. Unfortunately, I do not have concrete results between the interaction of glaciers, climate, and archaeology in the tropical Andes. So I will show you another example from Greenland. It's a bit far, but at least it should be interesting for you. Let's start. I like glaciers because we are able to study climate for sure, but glaciers are also useful for different purposes. First, in different cities like here in La Paz, the ice melting and snow melting is useful for clean water. This is the same in La Paz. You have the same situation in Peru, like Lima or Quito. But another point, it's here we are at 5,800 meters, and you have a dam. This dam collects waters from Zongo Glacier, which is also located in Bolivia. And of course, this dam produces electricity for La Paz city, but it's again the same story in different countries of the tropical Andes. Okay. Another point that you certainly know better than myself, glaciers are sacred objects for local people. On the left, you can see women praying for a better crop. And on the right, you have two pictures. On the top, you have two glaciers. Again, it's in Bolivia. You have Illimani here and Mururata on the left. And you can see that the surface of these glaciers is totally flat. And the legend says that there was a war between Earth and Sun. The two entities were represented by different glaciers, Illimani and Mururata. There was a fight, and the head of Mururata was rolling on the Altiplano, and it created Sajama, which is the highest volcano in Bolivia, and we made some ice cores records on this summit. So the basic the aim of this presentation is to show you some basic knowledge about glaciers and climate interactions. We study the evolution of the glaciers for the current period, but we also focus on the past. We covered at least the last 20,000 years, but I will insist on the Holocene period. And as told you before, I will show you another example from Greenland. So the tropical Andes cover only a small surface of ice. This is not the point. The point is we can study glaciers for climate change, but also for different purposes, as I told you before. Another point that you have to consider here, the mass balance, it's a classical metric in glaciology. So just remember this name. This is very simple. Mass balance is a direct link with climate. What is it? Okay, it's simple. It's just the difference between the snow, which covers the highest part of the glacier, minus the snow and the ice, which has melting, has melted at the end of the year. On the right, you have a picture of the glacier. You have on the top a white surface. What is it? It's snow and ice. Below, you have a dark surface. What is it? It's just ice, which is covered by dust. So at the end of the year, we measure the difference between snow on the top and snow which has disappeared and ice which has disappeared at the end of the season. And this is the mass balance. When the mass balance is positive, the glaciers is growing. When the mass balance is negative, glaciers are retreating. Where we do that? we do that in different countries, from Bolivia to Colombia. You have a list of glaciers that which are surveyed by the Great Ice team on local partners. It was me when I was young in Bolivia. This is another picture from Ecuador. And so what do? We measure mass balance measurements, but also length changes, area, different aspects to measure mass balance, and also ice core records that were collected, for instance, in Bolivia, in Peru, in Ecuador, and some tentative in Colombia. What do we know about glaciers over the current period? Of course, glaciers are melting. You have a situation for Chacaltaya Glacier, which is also located in Bolivia. You have the situation in 1940. It was in 2005. Now we do not have ice anymore. The glaciers have disappeared. Okay, you know that. In 2013, we made a review of with different partners from Bolivia, Ecuador, Peru, and so on. And this, which summarized the most conclusion that were obtained by this survey. This was published in the Cryosphere. So one of the main feature of this analysis is given here on this graph. So you have some years here. So it's 2009 here. We should follow the line for the current period. And you have cumulative mass balance. So it's again the evolution of the glacier through time. And here you have different glaciers. I was speaking about Zongo. Zongo is here, okay? And you have two curves which correspond to the altitude of the glacier. Some glaciers are located at high altitude, and of course the melting is not so strong as for the glaciers which are located at low altitude, okay? It's just due to the fact that temperature impacts the snow rain limits on the glaciers. Sometimes it's raining, which is very bad for the glacier. Sometimes it's snowing, which is good for the glacier. And this depends on the temperature for sure. When the ice is melting, it produces water. So we also measure hydrological balance of different glaciers. Again, this is Zongo glaciers in Bolivia. And this picture was taken in Ecuador. What do we do with that? Another picture of that. At the bottom of this figure, you have September here and September here. So it's an hydrological year. And you have two graphs. On the top, you have hydrological events. And on the bottom, you have the glacier discharge, which is so the mass balance, but measured at the snout of the glacier, from which measure the ice, which has transformed in water. So what do we see? You have a classical situation of precipitation in Bolivia. You have the dry season during from May to let's say August. Then you have an intermediate season from September to October and November. Then the rainy season from December to March, April. And you can see that it's you have here the peak of the discharge of the glacier, and you can see that both curves do not match perfectly. Okay, you can see that the maximum of the rainy season does not correspond to the maximum of the glacier discharge. This is because of energy balances. On the intermediate season, you have clouds that have a strong influence on glacier discharge. But this is important because, of course, this has you can see that glaciers have a buffer effect on the hydrology on the valley. So it has a strong impact for agriculture for sure. Years ago, we were drilling high summits in different regions. I took this picture in 2007, when I was young. It's on the top of Sahama, and we drill this summit with Lonnie Thompson. And this is the bottom of the volcano. This picture was taken from another ice core record that we collected in Illimani a few years later. And you saw that, you know that Lonnie Thompson was the pioneer worker drilling ice core records from tropical Andes. And at that time, we believed that the isotopic variations corresponded to temperature changes, because we had at that time in memory what we know about isotope variation in Greenland or in Antarctica. But we are in the tropics, and the variation of temperature in the tropics are very small, so it doesn't work. Here you have two different figures. On the left, you have the delta-IAM excess with monthly rainfall, and you can see a clear relationship between both parameters, I mean rainfall and delta-IAM excess. And this was published in different papers. And on the right, again, two curves. Yes, please. Yes, sure. Yeah. Okay. Okay, anyway. On the right, you have two curves. You have a pink curve, which is, what did I do? Okay. So the pink curve corresponds to a combination between different isotope records from different ice cores, from Bolivia, from Peru, and from Ecuador, okay? And we mixed this to produce one curve. This is the pink curve, okay? And we produce a regional precipitation for different regions. And you can see there is a good correspondence between two curves, okay? So once again, initially, we believed that isotopic variation from ice core record in the tropical Andes were driven by temperature. This is not the case anymore. We believe that isotopic variation from ice core record show precipitation changes. Interesting. I think I need your help. Ooh, sorry. Okay. Yes, happy to know that. So I show you some results about the current variation, but we also study the past. And how we do that? It's not so easy, but by chance, glaciers, when they are flowing in the valley, they create some landforms. And the basic landforms that we can observe, it's these lines. And these lines correspond to landforms created by glaciers. These are moraines. This picture was taken again in Bolivia. It's Charquini Glacier, close to La Paz. So you have different lines. So it means that the glacier reached these positions when, this is the key point. I have to know that. How do we know that? We use cosmogenic ages, and I will explain afterwards how we calculate this, basically. When we know that the glacier reached this point, we have to, we can simulate the extent of the glacier, which means a lot of a volume or surface of ice. If the glacier was larger than today, it means that climate was different from today. So it means that we have to, we can simulate the past climate conditions that could explain the glacial extent in the past. Okay, so again, the same picture. So how do we know how can we date these lines, these moraines? So basically, we use different techniques, and one of the most famous one is cosmogenic dating. You have some fluxes from the sky, explosion from supernova that creates a nuclear reaction into the rock, and we will this produce isotopes into the rock, and we will measure this production. So it's a little bit complex. We have different chemistry processes, but at the end, we have a good chronology. This is the same glacier, but from IR photograph. You can see different lines which correspond to the different moraines. You have two different colored points. You have red points and blue ones. This corresponds to two different periods of time. In red, you have the late Holocene chronology, and in blue, you have the early Holocene chronology. It means that the glaciers came here some time ago, and when we calculate the mean of these different ages, we obtain the age of 450 years, more or less 73. Then, few meters away, we have another ridge, and this ridge was from the early Holocene again. You have the age of this all these samples that show to a large advance during the early Holocene. So I will try to show you the evolution of the glaciers in the Andes with this nice picture. As you can see, I'm a very good painter. Sorry for that. But I hope it will help you to understand the situation. So from the left to the right, you have the early Holocene here and the late Holocene on the right. On the top of this figure, you have the situation in the early Holocene. At that time, glaciers were large. It corresponds to the largest situation of the Holocene. And again, this is dated by cosmogenic ages that we collect in different parts of the Cordillera Real, but also in different countries. It's the same pattern. During the Middle Holocene, we have a climate change, and it was much drier, so glaciers were retreating. And again, during the late Holocene, the situation was changed, and the situation was wetter, and glaciers were growing again. This is the same picture, but a bit more complex that I will explain. You have two different things. You have blue colors and red colors, and you have also points with different sizes. The size corresponds to the size of the glacier. So it's easy. When it's large, it means that the glacier was large, and when it's small, it means that the glacier was small. And the situation is compared to the Little Ice Age. So again, I will take my glacier, which is located in Bolivia, Charquini Glacier. We know that in the early Holocene, the glaciers was larger than during the late Holocene. This is the case. And during the Middle Holocene, the glaciers has disappeared. But when we compare with other regions, in particular in the northern hemisphere, you can see that some parts of the North Atlantic regions, you have the same pattern, but in other regions, like in Himalaya, for instance, it's totally different. Again, in south of Patagonia, you can see that the glaciers were disappearing during the Middle Holocene in Bolivia, but it was not the case in Patagonia. So what are the reasons for that? We know that ENSO has a very strong impact on glaciers today. We know that. I will show you an example. Again, it's Zongo mass balance measurements from February 92 to February 2000. Okay, you have two lines. The first line here in dark corresponds to the mass balance of the glacier. So you have an evolution of the glacier from year to year, and you can see a very negative year during February 98, which a very classical Nino. And here you have the situation, the sea surface temperature from Pacific, on the east part of the Pacific, which is a good indicator of ENSO. Okay, and you can see that when in the Pacific the temperatures are very high, the glaciers are melting, especially Zongo. So you have an opposite situation when the situation is Nino or Nino-like, glaciers are retreating. When it's Nina, glaciers are advancing. Okay, I have probably my explanation of the situation in the past. Let's start. Again, my very famous picture. So I told you that glaciers were larger in the early Holocene, but data from coral records, ice core records on different proxies tell us that at that time it was Niño-like conditions. So it was warm with very famous and very strong Niños. And I told you before that when it's we are in Niño situation, glaciers are melting. So this is bad. Okay, it does not work. Let's start with the Middle Holocene. During the Middle Holocene, again, some proxies say, okay, Middle Holocene is Niña-like conditions. So wet conditions that should favor glacier growing. Again, whoa, it doesn't work. It's not the case at all. Let's start with late Holocene. Same things. It does not work at all. It means that for the Currian period, Niño has a strong impact. But when we focus on the larger time scale, it doesn't work anymore. So what is the main factor? Oh, the factor is AMOC. AMOC is Atlantic Meridional Overturning Circulation. It's the Gulf Stream, more or less. And you have here the circulation. Forget about these two pictures. Just focus on this one. This is a correlation between Zongo, which corresponds to the white dot here, with sea surface temperature at a global scale. And you can see that when temperature is cold here, there is a strong correlation here. And it means that when it's cold here, the mass balance is positive. How we can explain that? Again, another picture, you have precipitation from the early Holocene here to the current period here. And you have the precipitation expressed in anomaly compared to the whole period, whole Holocene period. And you have two curves. The first curves correspond to an output from the GCM climate models, which names trace. And you can see the situation here when we do not consider AMOC circulation. So it's more or less flat. Nothing happens. When we take care about AMOC change, you can see a strong variations of precipitation through time. And you can see two major periods of precipitation that occur during the early Holocene and during the late Holocene, and a dry period, very dry, during the Middle Holocene, and by chance it corresponds to the period of during which the Titicaca Lake was very low. Let's focus about temperature changes. I told you that. So again, you have the time on the at the bottom. The early Holocene is located on the left, and the current period on the right. And again, you have temperature variation expressed in anomaly with two different climate models. And you can see that during the Middle Holocene, the situation was very flat, but you have some variations which are not too strong, but you have more or less for the whole period less than 1 degree change. So again, the variation of glaciers in the tropical Andes is not mostly driven by temperature changes, but driven by precipitation changes. In 2013, I was talking about a paper that we published in the cryosphere. At that time, we made some lichens measurements on different glaciers from different regions, and we were able to estimate roughly the evolution of the glaciers in different regions, in Bolivia, in Peru, and in Ecuador. And we saw that it was more or less the same thing. We have a little ice age maximum and even an early little ice age. Then glaciers were retreating with minor stops that correspond to these triangles. At that time, the proxies that we could use to document the climate conditions in different regions were there were very few proxies, only 3 from ice core records. You have an evolution of a composite of different ice cores from Bolivia and Peru. When the curve is above the zero level, it's dry, and when it's below, it's wet. And you have the same situation for different curves. This is a situation from Calcarea again. So a wet period during the middle of the last millennium, then drier period, then a bit cooler and wetter period at the end of the last millennium. I will forget about this picture because we do not see anything. But this was in 2003. Then the situation has been largely improved. I show you a paper that was published in 2014, I guess, from Neukom et al. That shows you an evolution of temperature in the northern and southern hemisphere. You have in blue the evolution of the temperature from the southern hemisphere, and it covers the last 3,000 years. So this is the Currian period. You can see an increase in temperature. And this is the late Holocene period. You can see here the Little Ice Age, which is defined in the northern hemisphere. You can see that there are some strong difference between the northern hemisphere and southern hemisphere. But please consider the fact that, again, it's expressed in anomaly, but the evolution is quite small, only 0.3 degrees Celsius. This is a summary of different proxies that were published over the last couple of years from different regions, mostly from ice core records and speleothems from different regions of Bolivia, but also Peru and Brazil. You can see that some periods show a good matching, but for others, period is not the case because you have some regional variations of climate conditions, in particular for the precipitation changes, which is very frequent. But at least we have something. Now, with these proxies, we are even able to calculate hydrological consequences of for the valley. When you have a glacier which disappears, of course, you have consequences for the hydrological balance of the valley, and we can even produce some more sophisticated scenarios in considering change in temperature, precipitation, short and long wave radiations, and even clouds. Just two pictures that could be interesting for this purpose. I show you some example of a cosmogenic application for the moraine records which is shown here on this picture on the left. But I'm currently working on Abbaye Mont Saint-Michel, and we are trying to date this edifice. Of course, we know more or less the date of this edifice, but we are trying to constrain the cosmogenic method to apply it to different very famous buildings. And of course, this technique was used to date some lithic tools in the past. This could be useful for some of your buildings. I'm not saying there are some no issues for sure, but maybe we can try. This is the end of my talk. I will show you some pictures of Greenland, and I hope to convince you that glaciers can be useful to understand some key questions in archaeology. I will focus on the Viking period, the Norrois, and I will show you how glaciers can help to understand the dynamic of the Viking in this region. Again, this is the evolution of temperature in the Northern Hemisphere from Pages 2013. It was published in Nature. You can see two different periods, a warm period, which is a medieval climate anomaly, and a cold period, which corresponds to the Little Ice Age. You can see some large differences in temperature, which is totally different from Bolivia, for instance. This was done at a hemispherical scale. Now, we have the same for different latitudes. And this on red, it's the same curve as I showed you before. And in dark, you have another reconstruction from Kaufman et al., which combines different proxies from only the high latitude of the Northern Hemisphere. And you can see that during the medieval climate anomaly, you do not have the same amplitude of variation. Okay. What do we know about medieval climate anomaly in Europe? Of course, glaciers were very small. We know that people were producing wine in England. We don't know if this one was good, but at least they produces. We know that Viking invade Greenland at that time, and the hypothesis says, okay, because the Viking came in Greenland because climate was warm, okay? And you have some yellow crosses that correspond to the Viking settlement in south of Greenland. What do we know about the Little Ice Age? You know that better than me. You have on the left a picture of Bruegel D. Hall 1 that shows you snow in Holland, and this is another picture from La Mer de Glace in the French Alps in the 19th century, which of course was much larger than today. So at the middle of the last millennium, Vikings disappeared from Greenland because it was too cold for them. At least it's one hypothesis. Okay, because it was the Little Ice Age, and some publications said, okay, it was too cold. They were not able to survive to this dramatic cold period. Let's examine this hypothesis. So we work in different glaciers far from the ice sheet, which is here. I don't know if you can see some red points from the end of this room, but these red points correspond to settlements, Viking settlements. So we were very close to these settlements. We were working on moraines. Again, these lines. We simulate the extent of the glacier, and we estimate paleoclimate conditions that could explain this larger extent. Let's try. Here are the results of the cosmogenic ages we collected from the samples, from the moraines. And what do we know? We see two different advances. One at the beginning of the last millennium, and another one during the middle of the last millennium, during the Little Ice Age. So when I summarize, I have one advance during the Viking colonization and another advance during the abandonment of the settlement. Let's estimate the climate condition responsible for these two advances. When we use our climate and glaciological models, the first advance could be explained just by decreasing the temperature of 0.65 degrees, 0.65 degrees. And the second advance could be explained by a decrease of 0.6 degrees, 0.6 degrees. So the first hypothesis was, okay, it was too cold for Viking to survive to a very cold temperature. I say, I'm not sure it's a good reason. 0.6 degrees is, in my opinion, not too cold, and they probably have different. There were probably different explanation, but climate was probably not the single driver of this abandonment. To prove that, I show you two different climate reconstructions. This is an observation of precipitation from Meteo Narsarsuaq during the 20th century. And you can see some large variation, but the trend is globally flat. And here it's temperature for the same meteorological station from the end of the 19th century to the 20th century to 2000. And you can see a clear trend. So it means that this variation, it's much smaller than what we observe today. So, in my opinion, of course, 0.6 degree is not nothing. It affects the growing season. It affects the duration of snow mantle. It affects also sea ice, so different aspects. But these have a strong impact on flooding. But this is not direct consequences of climate change that could explain the abandonment of Viking in south of Greenland. We have also different hypotheses that were published more recently, a war against Eskimo and the decrease of ivory, etc. This was my last slide. Thank you very much.